So the next example we're going to look at is the multiple angles example on your notes from 7-3. And what I've done right here is I have provided you a graph of y equals sine x. So there's our function y equals sine x. And here we are at y equal 1/2. Now, if you recall, the 2 theta here is going to affect the period of sine x, and so our period here is pi. But what I've done is I've scaled this out from 0 to 2 pi. So you can see that there are actually two of those sine curves from 0 to 2 pi. And so the solution to this equation, and we're looking for all of the values of theta in the interval 0 to 2 pi for which that equation is true, you can see that there are actually 4 solutions. And we're gonna find all 4, and we're gonna start by looking at the quadrant where our angles are going to lie, and doing some multiple angles from there. So I'm going to start, I'm just going to rewrite the equation by, again, using the SIGN of our ratio, and because it's implied as positive, we know that the 2 theta angles will live in quadrants 1 and 2 where sine is positive. Our reference angle is going to be pi over 6 because that's where sine has a value of 1/2. And so we can see that 2 theta will have a value of pi over 6, and 2 theta will also have a value of 5 pi over 6. Oopsie, 5 pi over 6, because that's the second quadrant angle where sine is 1/2. So again, that's just for 2 theta, not for theta itself. We're going to add a revolution onto this. Well, we'll add several revolutions onto each of these angles. And then what I'm going to do is I'm going to solve for theta now. So theta is going to be pi over 12 plus pi n, or theta is going to be 5 pi over 12 plus pi n. So actually, when we're finished with this one, I'm going to show you another method that you can use for this, and you're welcome to pick a method that works for you. So now I'm focused on theta itself, and recall from example 1, from the linear methods, that we define n for all integers. So I'm going to start letting n take on some integer values, and I'm going to start with n equals 0. So if n is equal to 0 in this equation here, I know I have a value of theta that's equal to pi over 12. And if n is equal to 0 in this second equation, I know that theta has a value of 5 pi over 12. Now I'm going to let n equal 1. I'm going to go back to that first equation here. And if n is 1, then I'm looking at theta having a value of pi over 12 plus pi, or 13 pi over 12. And if I go back to this equation here, if n is 1, then theta will have a value of 5 pi over 12 plus pi, or 17 pi over 12. Now if I let n equal 2, I'm going to be over 2 pi. If n is 2 here, I have 2 pi plus pi over 12. I don't want my values of theta to be over 2 pi. So, oopsie, I didn't want to do that. So what that does for us is it gives us, I'm just going to move this up for a minute, it gives us values of theta that work for this equation: pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. And then what you're, just to confirm this, and again, we did this graphically, you can certainly use your graphing calculator to double check your answers. And again, that's just for you to gain confidence in your equation solving abilities. But if you go back into your graphing calculator and go to the table and let theta equal all of these values here, you'll see that your output is going to be a half. So that is method 1 for example A on multiple angles. Now I'm going to look at another method for doing the same problem. So let me start by writing out the example. Sine 2 theta is equal to a half. And again, our goal is to solve for theta in between 0 and 2 pi. So I'm actually going to build what's going to happen for 2 theta, and I'm going to multiply every part of this inequality by 2. And so what that means is 2 theta can live anywhere from 0 to 4 pi. And so I'm going to focus on 2 theta to start, and then I'm going to solve for theta. So again, I know that my 2 theta angles will live in the first and second quadrant. We already know our reference angle is pi over 6. So our 2 theta options are going to be pi over 6 in the first quadrant and 5 pi over 6 in the second quadrant. But I'm allowed to take those 2 thetas all the way out to 4 pi. So I'm going to add another revolution to pi over 6. That's going to get me back to this angle here, that terminal ray, and then I'm going to add the same thing to 5 pi over 6. I'm going to add a revolution, and so again, that's going to actually take me back to that terminal ray in the second quadrant. And so let me just simplify that. 2 theta can equal pi over 6, 5 pi over 6. What is this? 13 pi over 6 and 17 pi over 6. Did I do that right? Multiply by 6 over 6. Yeah, 17 pi over 6. Now I'm going to divide everything by 2. Right? So basically I have this giant four-part equation. And so if I solve for theta now, I have pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. And again, if you go back to your graph of sine 2 theta equal to a half, you can see that these 4 values are the ones that are going to satisfy the equation. Certainly go back and do a quick check, and I'll just check one of these solutions. Sine 2 theta, let me pick 13 pi over 12, equal to a half. We'll do some simplification. The sine of 13 pi over 6 is equal to a half. Let me scooch this graph up a little bit. We know that the sine of 13 pi over 6 has a coterminal angle with pi over 6, and 1/2 is equal to 1/2. See, that was messy. So your choice on the method that you'd like to use to solve these multiple angle equations. I actually kind of like this one better, but choice is yours.